Okay, welcome you all in this talk, and today we will discuss Urizen's lemma and then the continuity of function and compact spaces and the uniform continuity. So we start from the Urizen's lemma. So what is the Urizen lemma? To come to the statement of the Urizen lemma, let us define the separated sides by a continuous function. So suppose if you have you have a metric space, I write it is not necessarily the metric space should be like this. Suppose you have a metric space A and metric space B, a subset A and a subset B of the metric space X, and here you have the real line. So I have the closed interval 0, 1. So if you can find a continuous function from X to the closed interval 0, 1 such that the value of the function f, okay, for all x, f of x is equal to 0 if x is in X, and for all x in B, f of x is equal to 1. Okay, so if we can find a continuous function such that from the metric space X to closed interval 0, 1 such that f of x is equal to 0 for x in A and f of x is equal to B, f of x is equal to 1 for x is in B, then we say that A and B can be separated by a continuous function. Okay, so here is now the question is that under what condition we will have a continuous function that separates the sets A and B. So here is we are taking A and B are any two subsets of a metric space X. So the Urizen lemma says that if the sets A and B are disjoint closed subset of a metric space, then there always exists a continuous function from X to closed interval 0, 1 such that that separates A and B. That is, the value of the function is equal to 0 for X in A and f of x is equal to 1 for X is in B. So the Urizen lemma says that if A and B are two disjoint closed subsets of a metric space X, then there exists a continuous function that separates the sets A and B. Okay, so to prove this one, we will define a function rho xa. That is to say, we will define rho xa, that is the distance function from a point A to the set, from a point X to the set A. What is that? We have already seen that the rho xa is equal to the infimum of xy, and infimum is taken over y in A. So this is the distance function from the point X to the set A. Now we define a function f from X to closed interval 0, 1. Because we want to prove that if A and B are disjoint closed subsets of the metric space X, then there exists a continuous function such that this condition holds good. So we define a function f from X to closed interval 0, 1 by this one. That is to say, f of x is equal to rho xa divided by rho xa plus rho xb for all x in X. Okay, and then we will see that the value of the function, f of x is equal to 0 if x is in A. So if x is in A, x is in A. So if x is in A and A is closed, then we have proved in the theorem that the distance from the point X to the set A is equal to 0. It is true only if the set A is closed or if we take the closure of A. Okay, so the set A is closed, then by theorem this, so 1.4.1, this is equal to 0. So the numerator is equal to 0, it means that f of x is equal to 0. So f of x is equal to 0 for x is in A, and it is equal to 1 if x is in B. If x is in B, it means that the distance from x to B is equal to 0 again by this theorem. Because B is closed, so x is in B, so this distance is equal to 0. So rho xa upon rho xa is equal to 1. So we know that so f of x is equal to 1 for x is in B. Now we show that this function is well defined. That is to say, the rho xa plus rho xb is not equal to 0. If it is equal to 0, then this term can be infinity, and which is not, it means that the function f is not well defined. So to prove that it is well defined, we will show that this is not infinity. So if this is equal to 0, if denominator rho xa plus rho xb, it is equal to 0, and then both of them must be equal to 0, because rho xa is a distance, so it must be greater than or equal to 0, and rho xb must be greater than or equal to 0. So both must be greater than or equal to 0, and the sum is equal to 0. So both should be equal to 0. So then they must be equal to 0. But you see, x is in A, okay, and x is in B. So x is in A and x is in B. Then again by the same theorem 1.41, a contradiction, since A and B are disjoint. Because if this is equal to 0, it means that by theorem 1.4 and A is closed, so x must be an element of A. And this is equal to 0, it means that x is in B, because B is closed. So x is in A, x is in B, it means that A and B are not disjoint, and which is the contradiction of our hypothesis. Then we are considering A and B are disjoint closed subsets. So disjoint, so this is the contradiction, that A and B are disjoint. Hence we conclude that this function makes sense for all x is in A. Now, so we have defined the function, but we have to prove that this function is continuous. Okay, so as we have seen in example 5.1.3, that this function from x to r, okay, this function dxa, okay, this function and the function dxb, these functions are, of course, so this function is continuous. So this function is continuous. The sum of two functions is continuous, the quotient of the function is continuous, and therefore this is a continuous function. Now, if x is in A, then we have seen that rho of xa is equal to 0. So f of x is equal to 0 for x is in A. Also, if x is in B, then the denominator of the function f of x is equal to this thing, which is equal to rho of A, and hence f of x is equal to 1. And clearly, the value of f of x lies between 0 and 1 for all x is in A. So we have proved that there exists a continuous function, okay, defined in this way from x to close interval 0, 1 for the A and B are disjoint closed subsets of x, and this continuous function separates A and B, and this is known as, this statement known as Urijan's lemma. Now, if f is a continuous function and A is a subset of, if A is a compact subset of x, then f of A is compact in Y. That is to say, the continuous image of a compact set is compact. So this is very important result. The continuous image of a compact set is compact. So we have to prove that the f of A is compact whenever A is compact. So to prove that f of A is compact, we have to prove that every open cover of f of A has a finite subcover. So to prove that, so for that, let us take f is equal to g alpha. Alpha is in lambda be an open cover of f of a, and then we will prove that this has a finite subcover. Then because f is continuous and E g alpha is open, so f inverse g alpha is open in X, because the inverse image, the inverse image of open set is open when the function is continuous. So this is open in X for each alpha in lambda. And now you can take A intersection f inverse g alpha. So A intersection f inverse g alpha is open in A. Okay. So this will form an open cover of A. And since we are assuming that A is compact, so it has a finite subcover. It means that there exists a finite subset J of lambda. So J runs from 1 to n of lambda such that the A is equal to the union of K runs from 1 to n A intersection f inverse GK, because this is your finite subcover. So, and now because A is independent of K, so you can take A is outside from the union, so we can write in this way. And now this is equal to A intersection f inverse union of this one. Now it means what? It means A is a subset of f inverse K runs from 1 to union of K runs from 1 to n GK. And now operate A both the sides, then f of A is a subset of the union of GK, K runs from 1 to n. It means what? It means that G1, G2, Gn, this is a finite cover of f, and hence f of A is compact. The corollary is that if f is a continuous function from a metric space X to a metric space Y and X is compact, then f of X is bounded. So very simple that because f is continuous and X is compact, so f of X by the definition continuous image of compact set is compact, so f of X is compact. So every compact subset is bounded, closed and bounded, so this is your closed. Now the second result says that if f is a continuous function from a compact metric space X to a metric space Y, then f of capital F is closed whenever capital F is closed in X. So capital F is closed in X and X is compact. So every closed subset of a compact set is compact and F is continuous. So f of F is compact and every compact subset is closed and bounded. So this is your closed. So f of F is closed whenever F is closed. Now we have a theorem. We say that if f is a continuous function from a metric space X to Y and this continuous function is bijective and X is compact, then f inverse is continuous on X. In other words, you can say that if you have a bijective continuous function defined on a compact set X to a metric space Y, then there exists the inverse of f which is continuous on Y. So the existence of f inverse comes from this because f is bijective. So since f is bijective, the inverse exists. So since f is bijective, f inverse Y from X exists and hence also bijective. Now you have to prove that this is continuous. So this is continuous. So for that, inverse image of closed set is closed. So take capital F is a closed set in X. Okay. Then inverse image of this. So f inverse of this f is equal to f of capital F. Okay. Then we have proved that if X is compact, and in this theorem we have proved that this we have proved that f of a is compact, and therefore f of x is closed in Y, and hence the image of a closed set is closed, and hence f inverse is continuous. Now, you see that whether this theorem holds good when X is not compact. So, in general, if X is not compact, then f inverse need not be continuous. So, here is the X. Of course, if f is bijective, then f inverse exists. But if X is not compact, then f inverse may not be a continuous function on Y. So, to consider this one, we can to check this statement, we can consider an identity function I from a discrete metric space, or you can say that the real line with the discrete metric to the real line with the usual metric. Okay, so I is the identity map from the set of real numbers with the discrete metric to the set of real numbers with the usual metric. And then, because in the discrete metric you can see that the identity map is continuous. Identity map is continuous in the sense that because every subset of a discrete metric space is open. So, whatever you take any subset here is and take the inverse image, you will get in R. And because in R with respect to the discrete metric is open, so it is open in this space. But f inverse is so f inverse is continuous. But f is the ai inverse I is continuous, but I inverse is not. Now, the exercise is that give an example to show that the theorem this theorem, okay, where does not hold good if X is not a compact set. So, similar example you can see as I have mentioned here. Now, we have a very interesting exercise which says that if f is a bijective continuous function from a metric space X to another metric space Y, and if A is a non-empty dense subset of X, then the image of A under F is also dense in Y. Now, here is we have proved that the continuous image of compact set is compact. Okay, but in the continuous image where the function may not be bijective, we are taking any continuous image. The function need not be continuous. To have that the image of dense set is dense, the continuous image of dense set is dense provided that the function is bijective. So, here is you can see we have to prove that this is dense set. This is dense set means it has this the closure of f of a is equal to whole space Y. So let us prove, suppose A is dense subset of X, then we need to prove that f of A is dense in Y. F of A is dense in Y, that the closure of this is equal to Y. But Y is equal to f of X because the function is bijective. So, the range f of X must be equal to Y. Okay. Now, we want to prove that f of X, so let us take Y is an element in f of X. That is to say, Y is an element, small y is an element of capital Y. Any point, and consider an open sphere S R Y. That is the open sphere with center at Y and radius R. Okay. And now, since this is open and f is continuous, so continuous image of open set is open. So, f inverse S R Y is the set of all points such that f of X is in an open sphere with center at Y and radius R. Okay. So, this is your open set. because this is your open set and the function f is continuous. So continuous image of open set is open. So this is open. And now since A is dense, okay, then we have proved in theorem 3.21 that if A is dense, then it intersects with every non-empty subset. Then it intersects with any open subset. So it means that this is your, so A is dense, so the intersection of this with A must be non-empty. So this is non-empty, so let us take a point x in this set. Okay, and then we can operate x both the sides. So f of x is equal to f of this one, and so this is equal to what? This is equal to the open ball with center at y and radius r intersection f of A. It means what? It means that this is non-empty. So the open ball with center y, radius r and f of x is non-empty. It means that what? It means that y is the limit point of f of A. So y is the limit of point of f of A means that y lies in the closure of f of A. So we have taken y is an f of x and it is a subset of this one. It means that this is a subset of the closure of f of A. So this is holds good. But the reverse always holds, and therefore a closure of f of A is equal to f of x and it is equal to y. Okay, and therefore we have proved that the f of A is dense in y. Now, what about the nowhere dense set? Can we say that if f is a continuous bijective mapping from a metric space X to a metric space Y, then the image of nowhere dense set is nowhere dense set? So it is not true. So if A is nowhere dense set, then f of A may not be nowhere dense set. So for that you will have to produce some example to show that if A is nowhere dense set and f is continuous bijective function, then f of A is not nowhere dense set. So just I have given the hint here. You can try first by yourself. If you could not succeed to give the example, then you can see here is. So you can consider the usual metric space R and set of rational numbers Q. Okay, and then you take A is the set subset of R2. Okay, consisting in the first argument the set of all irrational numbers and 0. So that is to say set of all irrational numbers on the x-axis. And if M is equal to A union Rn 1 over n. Rn is NL is a rational numbers. Okay, is subset of R2 with the usual metric space. And then you define a function projection map f from x cross from R cross F to R. So in this way that f of xy is equal to x, and we have seen that the projection map is a continuous bijective function from M to R, and you take A is a closed nowhere dense subset of M, while f of A is equal to R any set of irrational numbers, okay, which is dense subset of X. So here is it is just I have given the hint, and you can complete this proof by your own. Then we have which it is basically I have put it this as an exercise, but you can also treat this as a theorem, as an extreme value theorem. We say that every continuous real valued function defined on a compact set is bounded, and it assumes maximum and minimum values. Okay, that is so let f is a function, let f be a function from x to r, okay, be a continuous function, and A is your compact set. Then we have to prove that f of A, then by the theorem, the f of A is a compact. Okay, compact subset of R. So, compact subset of R, and then by Horn-Borel theorem, every compact subset of R is closed and bounded. So, f of A is closed and bounded. This means that the supremum of f of A and infimum of A f of A exist, and the supremum and infimum of f of A belong to f of A, and therefore there exists x tilde and x hat and x tilde in A such that for all y in A, the infimum of f of A, which is equal to f of x tilde, is less than or equal to y, which is less than or equal to f of x. Here is this f of hat x tilde is equal to supremum of f of A. So, this way we can prove. Similarly, you can prove that if x is a metric space and A is a compact subset of x, then prove that for every x naught there exists a y naught in A such that d x naught y naught is equal to the infimum of this thing, that is equal to d x naught A. So, this can also be proved very easily. So, proof is already given here. I am not going into details since the proof is very simple. But you can see the other exercise. We say that if x is a continuous function from a metric space x to R, any that f is a real valued continuous function, then the set consisting all points x such that mod of x is less than R is open in x for all is greater than 0. So, this is open in R. So, you have to prove that if A is equal to this thing, so A you can write in this way. But this is what? This is the inverse image of the open set minus R and R. And this is your open set. This is your continuous function. The f is continuous function. So, inverse image of open set is open. So, this set is open. It means that this is open. So, this you can rewrite by yourself.